All right, we decided to build a little windmill, kind of a toy. It's going to be 36-inch diameter, so 1 yard. We're not going to build the whole thing in this video. I'm just going to talk briefly about what we're starting with and kind of how we've designed it. But it's going to be a dual rotor axial flux alternator, meaning we're going to have two steel discs loaded up with magnets facing each other, so that the magnetic field will come out of one magnet directly into the other with really strong flux from magnet to magnet, and the path of the flux, the magnetic field, will go out the back of the magnet into the next magnet. So as we're putting the magnets on the disc, there'll be opposing poles next to each other. So we'll have north-south around. On this one, I'm going to put 8 magnets. These are neodymium iron boron magnets. They're the strongest kind you can get. These magnets are 1 inch diameter and 1/4 inch thick. The steel discs are 1/8 of an inch thick. The idea being that it's a good path for the magnetic field, for flux. We don't want it saturated, so I don't want to really notice a magnetic field on the back. As long as I can't detect magnetism on the back of the disc, it's good. The separation between the discs is critical. If it's too far, the flux becomes weak, and it will induce less voltage in the coils. So you wind up with a thick coil with high resistance that's not optimal. The optimal thickness of a coil is usually about the thickness of a magnet. So we're starting out with steel, magnets, some copper wire that we'll make coils out of. I've already wound a couple of coils. These are just a little over 1/4 inch thick. And before I started, I designed all this down here. I laid it all out with a compass. So this is a magnet rotor. It's 4 inch diameter with 8 1-inch magnets around it, spaced evenly. And this will be the stator, and I'm going to have 6 coils. So this will be a 3-phase alternator. If I wanted single phase, I'd have a problem, because I could do 4 coils, but if I had 8 coils, there wouldn't be any room for copper. The hole in the coil should be about the size of the magnet. So in this case, I really crowded magnetic material in here, and I decided to go with 6 coils so I could have 3-phase, and these coils fit nicely with the design. If I wanted to design a single-phase alternator, I'd probably run with maybe 6 magnets and 6 coils, or 4 and 4. But I want 3-phase for a variety of reasons. This is a magnet rotor that I've kind of faux together. It's going to come back apart, but I put the magnets down. I could have made a template, but I found that these popsicle sticks make good spacers, and they're pretty much perfectly spaced. And it turns out that I don't want the magnets flying out at high RPM. I could glue them on here, but my experience has told me that at high RPM, over 1,000 RPM maybe, with a blade this small, it might run faster than that even. I want to contain them. So I found these lids that fit nice around this, and I'll put them in here, and then I'll put epoxy all around in there, and the magnets should not fly out at the speeds we're dealing with. When I wind the coils, I'm going to make a stator. I'll probably make this piece out of wood, and I'll cut a hole in the middle, and the coils will exist in here, in this space. There'll be 6 coils in here going around. probably glue the coils to some very thin plastic, or I could just cast them in there with resin, but that's my plan. The engine for this alternator that we're building, well, before I get into that, I'll talk about the bearings. Of course, I could put all this on a shaft of some kind and somehow suspend this in the middle. That's definitely an option. I might do that. But what I'll probably do is make another piece just like this out of wood or steel, probably steel, and I'll put a spindle in it, either 3/8 or 1/2 inch, and I'll make a little hub that fits in here out of wood or metal and fit a couple of bearings that'll probably live either back here or inside. So this will all spin on a spindle. And the stator will be suspended in the middle between the rotors off a back plate on threaded rod. And this will look a lot like the bigger windmills I build. And I'll make another video when we get all this together in a day or two. Well, it might take me more than a day or two to get the video open. In this case, to keep it simple, I'm going to just make the blade out of a 1x4. I've already cut the width of this blade. I found a nice piece of 1x4. So it's about 3.5 inches in the middle, 1.5 inches wide at the tips. The skinnier I make the blade, the faster it's going to want to run. I could get very scientific with the airfoil and see that the angle of attack is correct at a specific tip speed ratio. But I find that, and a lot of other people have found that small wind turbines like this never run quite at a constant tip speed ratio. So I'm fudging a lot of this. The way I lay this out, on the back of the blade, if you look closely, this is the front, this is the back, this is the leading edge, meaning this, it turns this way. I've made a line 1/3 of the way back and another line 1/2 of the way back. And the way I like to lay these out, most of the material that I'm going to remove from this blade, see, somewhere in this piece of wood is a perfect windmill blade, and the goal is to try to find it by removing material. So to figure out how to do that, first I'll lay these lines out, 1/2, 1/3. 1/3 of the way back from the leading edge and 1/2 the way back from the leading edge. Now on graph paper I laid it out and I drew this double scale. And I'm only going to look at 3 parts of the blade to keep it simple. I'm going to look at the tip, I'm going to look at the blade halfway, and then the root. The pitch of the blade, meaning the angle, will get steeper as we move in towards the center of the blade. Reason being, that part of the blade is going more slowly. If the wind is coming at the blade this way, and the blade's moving this way, the actual wind that the blade sees, or the airfoil, is a combination of these two things. So the wind is coming at the blade something like this way when the blade is running around the right speed. And generally I want about 4 degrees here, give or take. And on a blade like this, there's a lot of give or take. But if that makes sense, this here is the wind. This is the direction of rotation. And if I could picture this as vectors, like that's the wind. And if my blade was running at a tip speed ratio of, say, 5, I could draw a line here 5 times longer. The blade's spinning this way, the wind's coming this way. So the blade is experiencing wind coming from this way. And that's called the apparent wind. And this here, this angle, is the angle of attack. The pitch of the blade is between this and the actual angle of the blade. And the idea is that the blade should live in here somehow with the correct angle of attack, which is usually about 4 degrees, give or take. So I kind of worked that out. I'm figuring these blades are going about 6 times faster than the wind. I kind of do that math, and I like to use graph paper and vectors. And I figure at the tip, I get this pitch here, and I actually draw it out with a protractor on the graph paper. And then I measure this distance here and here, and here and here, and I mark it on the wood. I make marks there. Do the same thing at the middle of the blade, which is going half as fast. So when I figure that one, this stays the same, but that becomes half. So the angle becomes steeper. So I recalculate that there. At the center of the blade, at the very center, to be correct, the wood would have to be infinitely thick. So we don't worry about infinitely thick boards. My board is only 1/4 of an inch thick. So at this part of the blade, I'll just make the pitch pretty much the full thickness of the board and get as steep as I can. It's a compromise I have to make. To get a nice shaped airfoil, we had this mark here 1/3 of the way back. The airfoil ought to be about 1/6 to 1/8 as thick as it is wide. So if I was, say, 6 inches wide, the thickest part of the airfoil, 1/3 of the way back, ought to be 1 inch. So that'll be the thickest part of the airfoil. So that'll be the curved part of the airfoil is going to come up to that. The halfway mark, I leave that flat, and that's undisturbed wood. I'll never touch that when I carve. And then from here to almost the very trailing edge, I might leave 1/8 of an inch here, not much, but I'll just plane that flat. Once all that's done, finish sanding, I'll kind of knock this corner off, knock that corner off, knock this corner off, and it'll come out a nice rounded airfoil. And I just do that at the tip and work it down to the middle and then to the root. And then I arbitrarily pick something like this or whatever and make a curve so I can escape in my carving back to the original board. I don't know if that makes some sense, but that's a real fast rundown how I've designed this blade. And to carve this, you know, a spoke shave or chisels, there are a lot of ways to carve this material out. Once I get out to about here, it's easy to use hand planes or a draw knife, or if I'm careful, I can use a power planer and make really quick work of this. Pretty easy to carve a blade. I've actually done a 3-blade set that's 20-foot diameter in one day with the power planer, and it came out pretty good. So carving a wooden blade is not hard. But that is kind of the plan with this wind turbine. The bearings, how this is fastened, the tail, that's all stuff I'll figure out later. And that's about it for this. I'm going to end this video here about now, and then we'll shoot another video about how we wind the coil. For this little wind turbine, it's pretty easy, but there are a few tricks. So that's all, folks. Fine, I'm back. I didn't make it clear enough.
This view here, if I'm looking from the tip of the blade, can I see that? if I were to be looking at it like this,
Uh-huh.
so then I would have leading edge.
This is the back of the blade. So the back of the blade is the one I made the marks on.
Okay.
So this is the back of the blade. This is the leading edge. Can't see the pencil. This is the leading edge. Leading edge here. So I did the cut on the trailing edge. So the blade is gonna, the airfoil is gonna exist something like that's the leading edge. Airfoil is going to live about there like that. That'll be the blade. This is 1/3 of the way back. And this is 1/2 of the way back. So 1/3 is the thickest part. I won't disturb this little area in here, and then that gets carved off flat, and that gets rounded, and this will be about a 2 to 3 degree pitch here off of parallel with the board or the direction of rotation. Does that make sense? And then that will get steeper as it goes in, and it should get exponentially steeper. But in this case, it's going to get kind of linearly steeper halfway in, and then it's going to get steeper as much as possible as we approach the root. But, and to clarify some definitions, the root is the center of the blade. And so, also it's interesting, and there are some very good blades, like Berge wind turbines. Some of their blades don't have any taper at all, but good wind turbine blades ought to, but turns out that blades that don't seem to work pretty well too. Some of their blades don't have any twist at all. They keep a constant pitch all the way down, and it's only because I look at blades like that, like Berge blades and some old wind charger blades I've seen that work really well, that I know I can get away with murder in blade design. So this is a compromise. It's somewhere maybe a little bit better than that, but not as good as a mathematically perfect blade. And it's easy to carve. So there are a lot of compromises made to work from a piece of wood that you can get off a shelf and keep it easy to carve and design, while also trying to be sort of aerodynamically correct. That's all. Thanks for letting me share.